The James Webb Space Telescope is set to answer many key questions that have fascinated astronomers for the past 50 years. With a $10 billion investment, it stands as one of the most ambitious engineering feats ever undertaken. Its mission is monumental: to change our understanding of the universe and redefine humanity's place within it. After traveling 1.5 million kilometers, the James Webb Space Telescope reached its destination, the Sun-Earth L2 Point, a special spot in space. To get there, it performed a precise maneuver called MCC-2, which lasted just about 5 minutes but was crucial to push Webb into its orbit around L2. This orbit is massive, even larger than the Moon's orbit around Earth. Over the next 6 months, Webb will be busy orbiting L2, adjusting its mirrors, calibrating its instruments, and making its first scientific observations. So, why is L2 such a big deal? It might seem like just an empty point in space, but it's far more than that. Despite being a place with nothing there, it's a vital location for Webb to operate and fulfill its groundbreaking mission. Let's find that out in this video. The James Webb Space Telescope, or JWST, finally launched on December 25th, embarking on its journey 930,000 miles from Earth. It represents the next generation, set to replace the iconic Hubble Space Telescope. Hubble has been delivering stunning photos for over 30 years, but now it's time for an upgrade. The JWST will use its advanced infrared sensors to explore the most distant and elusive parts of the sky, aiding the search for exoplanets and uncovering the early days of the universe. This is a perfect moment to delve into the key scientific concepts behind space telescopes. Though it might seem strange, empty space often has objects orbiting it. When two massive bodies orbit each other, they share a common point called the center of mass. If these bodies are large, this point lies between them. For example, the Moon orbits Earth because their center of mass is inside Earth. Pluto and Charon, having similar masses, share a common point between them. So, it's not unusual for objects to orbit empty spots in space. But how can Webb orbit a point beyond a two-body system? Let's break this down. Various spacecraft, like NASA's WMAP and ESA's Planck, have orbited the L2 point. Understanding how L2 works helps explain how Webb orbits it. L2 is one of 5 Lagrangian points in the Sun-Earth system. These points exist in any two-body system. Placing a third object at these points keeps it stable due to the combined gravitational forces. As the system moves, the third object moves along. For instance, L1 is great for missions that need to face the Sun or Earth. L2 is perfect for astrophysics missions like Gaia and Webb, ensuring continuous communication with Earth even as Earth orbits. Webb finds L2 crucial because it shields from the heat of the Sun, Earth, and Moon with one shield, which is ideal for infrared astronomy. However, certain conditions must be met. The third object's mass must be much smaller than the larger bodies. Webb's mass is tiny compared to Earth or the Sun. Additionally, Lagrangian points are best described as metastable, especially the first 3, similar to a frictionless saddle. Imagine trying to balance a marble in the middle of a saddle. It's tricky, right? That's how challenging it is to keep something at the L2 point. Picture this. An object initially moves toward the center, but then it wobbles back and forth, moving toward or away from Earth. If our space telescope Webb drifts away from Earth, it would be a big problem. We'd have to turn it around and fire thrusters, but that heats things up too much, ruining the mission. Plus, Webb's thrusters can only work on one side to keep it cold. The James Webb Space Telescope, or JWST, finally launched on December 25th and is now on its journey 930,000 miles from Earth. It's the successor to the iconic Hubble Space Telescope, which has captured incredible photos for over 30 years. But now, it's time for an upgrade. The JWST will use its infrared sensors to explore the most distant and hard-to-see parts of the sky, aiding the search for exoplanets and uncovering the earliest days of the universe. This is a perfect time to dive into the key scientific concepts behind space telescopes. So, what's the plan? We positioned Webb near the L2 point, but not exactly there. This way, if it starts drifting toward Earth, we can gently nudge it back into place. This careful positioning prevents Webb from drifting too far and getting lost. The precise Ariane 5 launch aimed to slightly miss the exact mark. However, being close to L2 brings challenges, like the Sun being blocked by Earth, meaning Webb can't fully rely on solar power. There's more to it. Webb will orbit around L2 due to Coriolis forces, and the Moon's gravity also affects Webb's orbit as it circles Earth. The trick is that Webb takes a large orbit around L2 to manage these forces. But how do you orbit around something that's essentially empty? That's the puzzle with L2. The James Webb Space Telescope, JWST, operates at the second Lagrange point, L2, a point of gravitational equilibrium created by the Sun and Earth. At L2, the combined gravitational forces of the Sun and Earth are balanced by the centrifugal force experienced by JWST as it orbits the Sun. When JWST deviates from L2, the balance of forces shifts. Moving away from L2 along the Earth-Sun line, the centrifugal force becomes stronger than the gravitational pull, causing JWST to drift further away. To counter this, JWST is repositioned closer to Earth, where Earth's gravitational influence can counteract the increased centrifugal force. Perpendicular to the Earth-Sun line, JWST needs small sideways adjustments to maintain stability, achieved through precise burns that keep JWST in an optimal orbit. The James Webb Space Telescope, JWST, maintains its position through precise orbital adjustments. Launched near L2 to avoid overshooting, it performs controlled burns to stay in a stable halo orbit, ranging from 250,000 to 832,000 kilometers from L2. This orbit ensures stability and the correct orientation for its sunshield and instruments. This orbit simplifies reaching L2, requiring minimal energy for navigation. It also avoids Earth's and the Moon's shadows, though it presents challenges like stray light interference and communication limits. JWST continuously adjusts its position to shield its mirrors and manage communication, ensuring successful mission operations. Webb spends about 6 months completing a single orbit around L2, sometimes extending a bit beyond this point. Despite this, its orbit's central focus remains on L2 prime, on the Earth side. It's important to note that Webb doesn't aim to be exactly at the center of the saddle-shaped orbit. Therefore, Webb performs small adjustments, called station-keeping burns, to maintain its orbit. While missions like Gaia need only 3 to 4 burns annually, Webb requires more frequent ones. This is partly due to its sunshield constantly experiencing pressure from solar radiation, causing rotational forces. Although Webb can counteract this by spinning its reaction wheels, the continuous solar radiation increases their speed over time. Eventually, a station-keeping burn is necessary to realign Webb and allow the wheels to ease off. Did you find this technique of keeping this telescope orbiting in space interesting? Then subscribe to our channel as we bring regular updates on technologies and theories related to space and our cosmos. Like our video and share it to more space enthusiasts like you. We will meet you in our next video with more interesting content on space science.